Infrared spectroscopy is one of the most powerful techniques for understanding molecules. But to really appreciate how FTIR works, we need to zoom all the way into the level of atoms vibrating like tiny balls connected by springs. If you imagine two atoms bonded together, they behave almost exactly like two masses joined by a small spring. If you stretch them apart, the spring pulls them back. If you push them together, the spring pushes back. This back and forth motion is what we call simple harmonic oscillation. That spring behavior follows Hooke's law, which is F is equal to negative kx, meaning the restoring force is proportional to how far you stretch or compress the spring. To visualize this more easily, we can plot a graph of displacement versus potential energy. What we get is a smooth parabolic curve, lowest at the equilibrium bond lengths and rising symmetrically as we either squeeze or stretch the spring. This curve is basically telling how much energy is required to pull the atoms apart or push them closer together. In the classical picture, this system can take any amount of energy as long as you keep pumping energy in the spring. You can make it vibrate with any amplitude you want. The more energy you add, the wider the oscillation becomes, exactly as shown in this energy curve. But this classical model hits a wall when we apply it to real molecules. Molecules do not vibrate with arbitrary amount of energy. You cannot just give the system a little extra energy and expect the bond to stretch proportionally. Instead, molecular vibration behaves like quantum harmonic oscillators, where energy comes in fixed, discrete packets, almost like rungs on a ladder. The molecule can be on the first rung, or the second, or the third. It can never land in between them. This is why infrared spectroscopy works. When a molecule absorbs IR light, it jumps from one energy level to the next. But the jump only happens if the energy of the incoming infrared light exactly matches the spacing between those quantized levels. If the light doesn't match the gap, even if it's close, the molecule simply ignores it and no absorption occurs. Now, even though molecules can vibrate in many different ways, not all of these vibrations show up in FTIR spectrum. A perfect example is carbon dioxide, or CO2. It has a symmetric stretch around 1330 cm, but we do not see any peaks there. But when CO2 performs its asymmetric stretch, which appears strongly around 2349 cm to -1, we do see an intense IR absorption. So this brings us to the IR selection rule, which is simpler than it sounds. A vibration is IR active only if it produces a change in the molecular dipole moment. So the molecule's dipole moment should change during vibration. This is the selection rule. In other words, the vibration must cause electrons' negative charge to shift towards or away from the more positively charged parts of the molecule. If electrons move unevenly during a vibration, that creates a temporary dipole, and infrared light can interact with it, can interact with temporary dipole. But if the vibration moves the atom in a perfectly symmetric way, when it's very symmetry in dipole moment, the electrons never shift towards one side more than the other, meaning the molecules has no change in dipole moment, and the vibration remains IR inactive. This explains why molecules like oxygen or nitrogen are completely invisible in infrared spectroscopy. They are homonuclear diatomic molecules. Both atoms are identical, and the electrons are shared symmetrically. Even when they stretch or compress, electrons move evenly, so the dipole moment stays zero. It's like they cancel out each other. With no changing dipole, infrared radiation simply passes through without being absorbed by a specific molecule. So now we know that to make a molecule vibrate, we must give it a very specific amount of energy that matches the spacing between its quantized vibrational level. And we also know that during this vibration, there must be a change in dipole moment for the vibration to be IR active and appear on the spectrum. But we haven't yet talked about what the molecule actually does when it vibrates. Yes, the dipole moment changes if the electron shifts, but we can look at how the atoms themselves move when we give the molecule the right energy. How exactly they move, what exactly they behave. That's what we can talk about right now. So molecules don't just stretch back and forth like a spring like you see in the earlier diagram or plot. So when we shine the IR light. So they also bend, twist, rock, wag, scissor, and deform in multiple ways. Every molecule with n atoms has 3n total degrees of freedom. 3 of these describe translation, moving the entire molecule through space. Another 3 describe rotation, turning the molecule around its center of mass. Everything that remains corresponds to vibrational motion. Everything that remains, other than rotation and translation, they correspond. That means they are the vibrational motion. That's why nonlinear molecules have 3n minus 6 vibrational modes, and linear molecules have 3n minus 5 vibrational modes. The reason linear molecules lose only 5 degrees of freedom instead of 6 is because one of their rotational motion does not count. Rotating a straight line molecule around its own axis does not actually change its orientation, which makes sense. That's why it's 3n minus 5. Let's take CO2 as an example. It's a linear molecule because the carbon is double bonded to 2 oxygens arranged in a straight line due to electron repulsion and molecular geometry. So we use the 3n minus 5 formula here because it's a linear molecule. 3 atoms multiplied by 3 dimensions gives us 9, and subtracting 5 leaves us 4 vibrational modes. So these 4 vibrational modes are a symmetric stretch, which is IR inactive, just like I mentioned it, asymmetric stretch, which is IR active, bending mode, also known as scissoring, it's also IR active, and then the other bending mode, which is rocking, which is also IR active. Because the symmetric stretch keeps the electron distribution perfectly even, it does not change the dipole moment and therefore does not appear in the spectrum, just like I mentioned it. The asymmetric stretch, however, creates an uneven shift in electron density between the 2 oxygen, so it becomes strongly IR active. Never forget, the IR always related to change of dipole moment. And both bending modes, one where the molecule bends like scissors and another where it rocks side to side, also create temporary dipole and therefore show up in the low energy region. It's around 667. Now imagine a much larger molecule such as caffeine has 24 atoms. So now we can calculate it. If it has 24 atoms, it has 3 times 24 minus 6, which is 66 vibrational modes. And every one of these vibrations could potentially be IR active if it produced a dipole change. That's why FTIR spectra of bigger organic molecules often look like a forest of peaks. Dozens of bending, stretching, twisting, and waggings, motions happening all at once, each one creating its own unique fingerprint in the spectrum. And I will show you the fingerprint towards the end of this lecture. Now, let's connect all of this vibrational physics to the instrument itself. In older dispersive IR spectrometers, you would scan one frequency at a time, almost like turning a radio dial slowly across the IR spectrum. But FTIR spectrometers do something far more elegant and efficient. And the heart of that system is Michelson interferometer. It's the key optical engine inside every FTIR instrument. It may look complicated at first glance, but the basic idea is surprisingly simple. Light from the IR source strikes a beam splitter, which divides the beam into two separate paths. One beam travels towards the fixed mirror, while the other travels towards the moving mirror. Both beams reflect off their mirror and then return to the beam splitter, where they recombine. And here is where magic happens. Because one mirror is moving, the beam traveling to the mirror experience a slightly different path length. So when the two beams recombine, their waves overlap in different ways, sometimes adding together, sometimes canceling out, depending on how far the mirror has moved and what wavelengths are present in the light. After recombining, this interference modulated light passes through the sample, which contains the chemical or molecular interest, often diluted in a solvent or embedded in a pellet or film, any sample. As the IR light interacts with the sample, only wavelengths that match vibrational transitions of the molecule will be absorbed, just like I explained it in the earlier video. Any bond or functional group that's strongly IR active will absorb more energy, causing noticeable drop in intensity at that specific wavelengths. Meanwhile, the detector does not see individual peaks or wavelengths yet. Instead, it sees the total intensity of this mixed interference signal change in the mirror moves. This time-dependent signal is called interferogram. At first glance, the interferogram just looks like a messy oscillating wave with no obvious meaning, but hidden inside it's a contribution of every wavelength coming from the source, combined into a single time domain pattern. This brings us to one of the most beautiful ideas in spectroscopy. Instead of separating wavelengths physically using a prism or grating, FTIR encodes all wavelengths at once into the interferogram and then uses mathematics to decode them. What's powerful about FTIR is that each peak tells us something unique. The positions of peaks tells us the vibration frequency, basically how stiff the bond is and how heavy the atoms are. The intensity reflects how much the dipole moment changed during the vibration. The shape of peak tells us about the environment of the bond, hydrogen bonding, or whether the vibration is coupled with neighboring bonds. In other words, an FTIR spectrum is like a full molecular biography written in vibrational language. When you put all these pieces together, the spring-like behavior of bonds, the quantized vibrational bonds, the importance of dipole change, and the number of vibrational modes, you get a complete picture of how FTIR spectroscopy works. It's not just a graph of peaks, it's a profound demonstration of the physics inside the molecules. FTIR let us identify functional groups, analyze mixtures, study reaction pathway, and understand molecular structure with incredible details. So when you look at an IR spectrum and see those sharp peaks at certain wavelengths, you're not just looking at the data, you're witnessing the quantum springiness of chemical bonds, each vibration singing at its own frequency. And that's what makes FTIR one of the most beautiful and insightful tools in spectroscopy.